Hey guys, and welcome to another fun and easy machine learning tutorial on linear discriminant analysis. Linear discriminant analysis, or LDA, is most commonly used as dimensionality reduction technique in the pre-processing step for pattern classification and machine learning applications. The goal is to project a dataset onto a lower dimensional space with good class separability in order to avoid overfitting, curse of dimensionality, and also reduce computational cost. Ronald A. Fisher formulated the linear discriminant in 1936, and it also has some practical uses as a classifier. The original linear discriminant or Fisher linear discriminant analysis was described for a two-class problem, and it was later generalized as a multi-class linear discriminant analysis or multi-discriminant analysis by C.R. Rao in 1948 for his research, The Utilization of Multiple Measurements in Problems of Biological Classification. Please subscribe and click that bell icon to join our notification squad. There are many possible techniques for classification of data. Principal component analysis or PCA and linear discriminant analysis are two commonly used techniques for data classification and dimensionality reduction. PCA finds the most accurate data representation in a lower dimensional space. It projects the data in the directions of maximum variance. However, the directions of maximum variance may not be useful for classification. Fisher's linear discriminant analysis, or just LDA, projects to a line which it inherently preserves direction that is useful for data classification. The main idea of LDA is to find projection to a line so that samples from different classes are well separated. Transformers. So as you can imagine from this diagram, let's imagine that these data points are transformers. Now you get the Autobots belonging to Optimus Prime's class,
Autobots, roll out!
And you get the Decepticons belonging to Megatron. Now if you apply PCA like our Minions example, we get a clash between the Autobots and the Decepticons. For you to easily discriminate between the transformer classes, we would use LDA to project these transformer data points so that the Autobots are linearly separable from the Decepticon classes. The mechanical alien data points are projected onto this new axis, where the axis was chosen to maximize the distance between the two means while minimizing the scatter for each class. So in a nutshell, often the goal of LDA is to project a feature space, which is a dataset with n-dimensional samples, onto a smaller subspace K, where K is smaller or equal to n-1, while maintaining the class discriminatory information. Principal component analysis versus linear discriminant analysis. Both LDA and PCA are linear transformation techniques that are commonly used for dimensionality reduction, as we mentioned before. PCA can be described as an unsupervised algorithm since it ignores class labels, and its goal is to find the direction, the so-called principal components, that maximize the variance in the dataset. In contrast to PCA, LDA is supervised and computes the directions or linear discriminants that will represent the axes that will maximize the separation between the multiple classes. Although it might sound intuitive that LDA is superior to PCA for multi-class classification tasks where the class labels are known, this might not always be the case. For example, comparison between classification accuracies for image recognition after using PCA or LDA show that PCA tends to outperform LDA if the number of samples per class is relatively small. You can check out a paper by A.M. Martinez et al. 2001 called PCA versus LDA. So in practice, it is not uncommon to use both LDA and PCA in combination. For example, PCA for dimensionality reduction followed by an LDA. Let's take a look at the LDA algorithm step by step. So the first step is to calculate the separability between the different classes, i.e. the distance between the means of the different classes, which is called the between class variance or between class matrix. The second step is to calculate the distance between the means and the samples of each class, which is called the within class variance or within class matrix. The third step is to construct the lower dimensional space, which maximizes the between class variance and minimizes the within class variance. The fourth and final step is to project our original data matrix using the calculated lower dimensional space, thus giving us our projected data. Now, the math in LDA is quite complex, so I'm not going to delve too deep into it. But if you want to get your hands dirty to understand LDA on a deeper level, I suggest you check out a paper called Linear Discriminant Analysis, a detailed tutorial by Ala Tarvat et al. It's a really great resource should you decide to code this from scratch and understand it on a fundamental level. Although LDA is one of the most common data reduction techniques, it suffers from two main problems. 1. The small sample size, or SSS. Singularity small sample size, or the undersample problem, is one of the biggest problems of LDA. This problem results from high-dimensional pattern classification tasks or a low number of training samples available for each class compared with dimensionality of the sample space. This can be possibly solved with regularization, or RLDA, or subspace and null space methods. 2. Linearity problems. LDA is used to find linear transformations that discriminates between the various classes. However, if the classes are non-linearly separable, then LDA cannot find the lower dimensional space. A way to solve this is to use the kernel functions or methods to map the original data into a high dimensional space so that data becomes linearly separable. We've seen this technique being used in our lecture on support vector machines, or SVMs. Applications. The use of linear discriminant analysis for data classification is applied to areas such as classification problems in speech recognition, biometric applications for feature extraction. In agriculture, an unknown sample can be classified into predefined species. For medical applications, DNA microarray data consists of a large number of features or dimensions. Due to this high dimensionality, the computational models need more time to train their models, which may be infeasible and expensive. Moreover, this high dimensionality reduces the classification performance of the computational models and thus increases its complexity. This problem can be solved using LDA techniques to construct a new set of features from a large number of original features. Okay, so that is it from me. Please don't forget to like, subscribe and share. Click the bell icon if you'd like to see more machine learning tutorials. And please don't forget to support us on Patreon, link in the description below. If you'd like to download the script to this video, please click the link down below to download for free. And stay tuned to the next lecture where we'll see how we can implement LDA in Python. Thank you for watching, and I'll see you in the next lecture.